Geometry, we're starting a new unit today. Okay, Unit 3. First, let's just talk about what is area. What do you think? I'd say most of you are going to say, all right, Miss Carly, it's length times width. Or 1/2, base times height. Or pi r squared. Well, what else is it? Okay. We can say it's a space. It's a set space. I don't know, it's where you measure something. Can't write. Measure something. I don't know, but we are going to talk about area today. If you look at this down here, it's on a coordinate grid. What is the area of the rectangle below? We have our side lengths measured 3 units by 5 units. If we counted all of the squares, we'd have to count big ones. If we counted all of these, we would have 15 of them. Make big lines. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But that's how you learned how to do area when you were young, right? As you got older, we taught you to multiply. And now we're going to talk about scaling an area. So here we have a 3/4 by 5/3 rectangle below. So to calculate this area, I would need 3/4 times 5/3. Okay, remember when I multiply fractions, I multiply straight across, so I have 15 over 12, which is 5 over 4 square units. What I want to point out here is we just calculated the area of 2 rectangular figures, and we used length times width to do so, right? Why can we use the formula length by width to calculate area of a rectangular region with whole number and rational side lengths? So what we used was whole numbers for the first example and then rational fractions for the second example. It works because those are finite values that I'm multiplying together to give me a finite area of a rectangle, right? So the area of a region, the area is a quantity that measures that region, this rectangle, okay? It's common to accept the phrase area of a rectangle to be the same as the area of a rectangular region, right? So we're going to push the limits of area a little bit in this lesson. Okay, area is a way of associating any region a quantity that reflects how big the region actually is. Sort of the, without even talking about shape, if we talk about area of something, it's a way that we can figure out how big a space is, right? Okay. In the examples that we gave you in the beginning, we had grid lines. In the first one, we had 5 times 3, and that gave us 15 square units. And then the next one, it was 5/3 by 3/4. Well, 5/3, I mean, that actually is like right down here, actually, yep. So that was the second example, because our area was 5/4 square units. So now we really see a sense of how big that area is. We can sort of internalize the difference between the two regions, right? Here's where we have sort of issues. Our exploratory challenge sort of prompts you guys to consider irrational side lengths. The square root of 3 doesn't have an end to the decimal. It's an irrational number because the decimal goes on forever and ever and ever, and so is the square root of 2. It's irrational. So what we're going to do here is approximate the area, because since they're both irrational numbers, we aren't going to get a nice solid answer that's exact. We are going to round, right? So if we did square root of 3 times the square root of 2, because that's length times width, we would get the square root of 6. Then you would get your handy dandy calculator out and crunch square root 6, and we would get approximately 2.4 square units, right? Sorry, I'm going to check that again. Yep, 2.4 square units. So, is our answer precise? Well, sort of. Square root of 6 is precise. Approximately 2.4 is not. Okay, let's talk one more time about irrational sides of a region, a rectangle. The one that we gave you in the last example was the square root of 2 times the square root of 3. Now let's actually look at, I got the calculator out and I took the square root of 2. And I rounded it to the 10th decimal place. I mean, I could round it more. Let's do that. And then the square root of 3, 1.73. Then I actually multiplied those, and I'll go ahead and multiply it again with the extra decimal place. 1.41 times 1.73. I got 2.43. That's actually a little better. The first time I did 1.4 times 1.7, 2.38. This time I'm actually at 2.44, which if you take the square root of 2 times the square root of 3 equals the square root of 6, and actually take the square root of 6, then you get 2.45, so that's much closer. But it just goes to hopefully show you that using irrational numbers as measurements and then using those numbers to calculate, you will not get an exact answer. You get an approximate answer, but it's not exact. It's rounded. It's close, but no cigar, right? So I'm just hoping you guys understand that. So let's take what we've learned about this figure and compare it to some upper and lower approximations. So for goodness sakes, how many times do I do that? Some upper and lower approximations. Okay, square root of 3 is 1.732. I'll just write a few of those numbers out, a few of those decimal places. Square root of 2, 1.414. We're going to use the decimal approximations to just show the difference between areas, sort of the upper limit of if we didn't round square root of 3, and the lower, or square root of 3 and square root of 2, and the lower limit if we didn't round it, right? So what I'm going to do is round this up to 2, right? So the square root of 3 will be up here. And at the same point, I'll go ahead and round this. This will be the upper limit, 2. Okay, area is way too big, right? So let me give you the lower limit now. This would be down to, we'll just go with whole numbers and 1. Okay, those are very, very rough and poor upper and lower approximations of that irrational side length triangle. Okay, let's go ahead and approximate a little bit better on the next one. Okay, again, same triangle. Let's do another approximation. Okay, let's tighten things up just a little bit more. So I've got the same square root of 3 and square root of 2 with the decimals out to the thousandth. And let's look at an upper limit of 1.8, which I'm going to shade in blue. That would be for the square root of 3, sorry, 1.8. And for the square root of 2, the upper limit would be 1.5. Erase that. Right about in half. So that would be our upper limit there. And then the lower limit, we go ahead and round down to 1.7. About in between. And then 1.4. A little shyer than that green one. So we're getting closer, right? Because square root of 3 and the square root of 2 aren't exact numbers. So go ahead and get closer and closer and closer. Let's try it one more time. So here we're going to try to zero in on the actual number square root of 3 and square root of 2 just a little bit tighter. So again, I've got thousandth decimal place out there. I'm going to do an upper limit, 1.74 by 1.42, and a lower limit, 1.73, 1.41. Because remember, these are not exact numbers. This is an exact number. So anytime I write out some decimal places, I'm doing an approximation, right? I can't put this into a fraction. It's not a finite number. So if I tried to draw this out to give you a lower limit and an upper limit, I actually can't. It's just my exactness in drawing with an iPad is just, it's not there. So that's just what we're doing between figure 1, 2, and 3 is zeroing in tighter and tighter on the actual value of square root 2 and square root 3. All right, approximations. So this is what we just did. So first, we looked at square root of 2. So we rounded it to 1. We rounded it to the lower approximation of 1, and then we added some decimals. 1.4, 1.41, 1.414, 1.4142, and we can keep on going. 41421. That was our lower approximation. We just got tighter and tighter and tighter into the actual value of the square root of 2. And then for the square root of 3, we got tighter and tighter and tighter into the actual value. And then if you actually do your multiplication, right? So we're multiplying these together. I should use. We'll see that our area approximation gets closer and closer to actual area. 1.41, 1.73, we're at 2.4393. And I'm just, what we're doing, if I have 2 decimal places here and I'm multiplying, I can have 4 there. If I have 3 and 3, I'm going to have 6, right? 2.449048. Keep on going. I mean, you guys can do this on your own. I have run out of room. 1.73205. Onward and onward. So we get closer and closer to an actual value. But this, even though there's so many decimal places there, is still an approximation. Can't spell. Oh, goodness. Can't erase. Still an approximation, right? Okay, upper approximation, same deal. What did we do? 1.5, we just kept writing out more and more numbers. 415, 414, 214. 1.732051. It's funny, I have to look those up myself. So if I multiply these two right there, I'll get that number. So we're zeroing in closer and closer. If you look on the previous slide, the lower approximation was also 2.449487. So we're the same for the last 4 decimal places, the 10,000th. Okay, so each successive approximation, each successive lower and upper approximation zeroes in on the actual value closer and closer. But we're never going to get to the actual value, right? It's too difficult to do. All right, so let's look at this problem. This is more of what your homework is going to be like. So if it takes 1 can of paint to cover a unit square in the coordinate plane, how many cans of paint are needed to paint the region within the curved figure? Okay, so I'm painting orange. 1 can covers a unit square. So how many cans do we need? Well, let's count squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. We're going to do half of this one and half of this one for 29, 30. I think I can do 31, 32, 30, oh, nope, 33, 34. So I got 34. Oh, and then I wrote a 2. 34, and then some. How do we approximate, these? All of this stuff on the outside that I didn't count. What do we do there, right? Yikes. So this strategy of just counting squares and half squares, it's going to take more than 34 cans of paint, right? Now what if we did something else? Now what if we consider the area outside the curve? This is sort of like the square root 2, square root 3 thing, where we had upper approximations and lower approximations. So we guessed on the outside of the shape and on the inside of the shape. Same deal here. Okay, we're sort of guessing on the outside of the shape and the inside of the shape. Let's count some squares. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, let's see, 33, 34. So in yellow, orange, we have 34. Okay? But I'm going to erase some yellow oranges. Minus 1, minus 2, minus 3, minus 4, minus 5. 29. Now, let's add like upper approximations. We're going to go here. I'm going to add 1, 2, right? 3. So 1, 2, 3, 4, 5, 6, 7, 8. Nope, we're going to do, 8, 9. You following me? 10, 11, let's see, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm going to add 20 blues. I'm at 49 cans of paint. So our answer is going to be somewhere between 34 and 49, right? I hope I counted that right. Oh, 49, 50, 51, 52, 53. Sorry. No. So, let's see. 49. I think I added 4. I hope I added 4 because I really don't want to go back and count it. So we are at, ooh, awesome, wrong pen. 53 cans of paint. Okay, I think I may have double counted something, but oh well, we are close. Somewhere between those two. Okay, but what if we tried something again? Hold on. Rather than you watch me try to count itty bitty squares, here we divided each unit square into 4 smaller squares. So if you look, this is no longer, this is my unit square. I divided it into 4 smaller squares. So 4 squares equals 1 can of paint, right? So here, if we counted them, there are 164 squares and half squares in the region inside the curve. So it takes 1 can of paint to cover every 4 of these squares, right? So if we divide, we would get 41 cans of paint to cover the region. Okay, but again, we still have all of these not covered pieces because this is our lower approximation. We're sort of underestimating, right? Underestimating. You'd hate to start painting a room and run out of paint. Trust me, it's happened. Well, here I'm overestimating, so I still have each unit square divided into 4 smaller squares. And if we look, each unit square is divided into 4, but I've also overestimated. So I've gone on the outside of the circular shape. So here I have 204 squares and half squares covered. So if you do your division, that is 51 cans of paint to cover the region inside the curve. So what's a good estimate for the area? I could keep dividing my curve into smaller and smaller unit squares, but that's just silly. Once I divided it into 4 pieces, I got 41 cans of paint and 51 cans of paint. So if we add those and divide by 2, I would need 46 cans of paint. That's a pretty good estimation, and it'll work. So there are some ways to determine the precise area of the curved region. We're going to save that for another lesson. At this point, this is what we're going to do, right? So in today's lesson, what did we do? We approximated area. By doing lower approximations and upper approximations. Okay, sort of rounding down and rounding up, a different way to say it. It's really a rough estimate when you don't know the exact size of something, right? When your shape is a curve and you're trying to find the area, or when your dimensions are irrational numbers and you're trying to find the area. More accuracy is found when you either use more numbers after the decimal place for an irrational number, or smaller smaller pieces, smaller unit squares for an irregular drawing. Right? So that's what we did today. We can practice this in our problem set. Good job.